Today we're going to implement logistic regression from scratch in Python, and this video is going to be quite technical and mathematical. We're going to not only implement it from scratch in Python, meaning we're not going to rely on any machine learning packages, we're also going to derive the mathematics from scratch. So we're going to start with a theoretical section where we're going to understand what exactly is happening behind the scenes when we do logistic regression. Even though the name is regression, it's actually a classification algorithm. We're going to understand how it works behind the scenes. We're going to derive all the formulas for the gradients and so on. Then we're going to do gradient descent, and then we're going to implement all of this in Python using only NumPy as an external package for efficient vector and matrix multiplication. Besides that, we're only going to use core Python. And as I said, this is going to be quite a technical and theoretical video. I already have similar videos for k-nearest neighbors, for k-means clustering, and also for linear regression. You guys seem to enjoy these videos, so today we're going to do logistic regression. Let us get right into it. Alright, so we're going to start, as I already mentioned, with a theoretical section where I explain the mathematics behind logistic regression. Now, you can of course skip this part and jump right into the code if you want to. I don't think it makes a lot of sense in this case because you're watching this video in order to understand logistic regression from scratch. If you just want to apply it, use the scikit-learn implementation of logistic regression, and that's it. You don't need to understand it. If you're watching this video, you want to understand it from scratch, so it makes sense to also understand the mathematics. I'm going to try to derive everything from scratch here, so we're not going to just take a formula, accept it, and put it into code. We're going to understand why the formula is what it is and what this means mathematically. You also don't need to be a math genius for this episode. You just need to understand some basic calculus and basic algebra. You need to understand what vector and matrix multiplication looks like. Or how it works behind the scenes, just a basic intuition. You don't need to do it by hand. And you should understand partial derivatives. So you should understand the chain rule of calculus. This is important when it comes to understanding how parameters influence the output and the loss function. But besides that, you're good to go if you understand math on a basic level. And you also don't need to understand everything to get the intuition. So if you just want to follow along a little bit and understand on a high level what is happening mathematically, you can also lean back and absorb the information. And of course, if you want to understand every single detail, take a piece of paper and a pen and try to derive it yourself while watching this video maybe. But I myself here have some paper stuff prepared just so I can take a look if I forget something while I'm explaining, which kind of happens sometimes when I record videos. But in general, as I said, we're going to derive everything from scratch, and we're going to do that in MyPaint, so my favorite visualization software here. And the first thing I want to cover here is the idea of logistic regression in general. So why do we call something regression when it's actually classification? Because logistic regression is used for classification, not for predicting things like stock prices or the weather or the temperature or something like that. We're not predicting actual values, we're predicting classes, so class indices. So why is this called regression then? The idea basically is that this logistic regression doesn't actually output a class label. What it does is it outputs probabilities, or in this case now we're going to look at the simple example with just binary classification. It's going to give us a probability, a number between 0 and 1 that indicates how likely the output is going to be 1, or yes, or positive, whatever you want to call it. So to take a very simple example, let's say in the case of an image, now we're not going to use this high dimensional type of data, but let's say we have an image of some animal, whatever this animal is, and this animal can be a cat or a dog, or we could also say it's a cat or not a cat. So it would be 1 or 0. That would be a typical binary classification example. You can also take any other data set as an example. You can take how long someone has studied and their previous grades and so on as input features, and then whether they have passed the test 1 or not 0. That would also be binary classification. So yes or no, whatever can be expressed as either yes or no, or cat, not a cat, which could mean automatically it's a dog, whatever. This would be an instance of binary classification. Now, what logistic regression does is it doesn't produce 0 or 1, it produces a value in between. So it gives us a value like 0.768, for example, which can be translated to 76.8% probability that we have a 1. So this would be a 76.8% probability that the image is a cat. This is why we call this regression, because we're actually predicting a value, a numerical value on a scale, so on a continuous scale, which means we're not just predicting yes or no, we're actually predicting the probability, and then we're taking that probability, we have a threshold, and we say, okay, if it's above 0.5, so if it's above 50%, we consider it a yes, so we say 1. That is then just the inference part, but the logistic regression itself outputs a value between 0 and 1, which is a probability. Now, how do we do that? We do that by just doing an ordinary linear regression and then applying a function that forces the values between 0 and 1. So what we have is we have some input, let's call it xi. So this is the ith instance, the instance with the number I. And this x is a vector, so it contains a bunch of features. For example, this could be a vector containing how long someone has studied, 20 hours, the previous score on a test, let's say 95 out of 100 points, and so on. We have a bunch of features. We have n features. So this would be feature 1, feature 2, and so on. And we could say this is just feature j, or we should call it xj for instance I, would be an individual feature. So that here would be x1 of instance I. So we have m instances, which means we have m different images of animals or m different students having studied for a certain amount of time, whatever. These are m separate instances, and we have n features. And features are things like how long did someone study? Then maybe a feature could be last test score. Then maybe hours slept or something like this, whatever. Just a bunch of features. We have n features and m instances. These are the x values. Now, what we do is we take these x values and we say, let's multiply them with a vector that contains parameters. Now, let's call this theta. And we can just say, okay, transpose theta. And what we get as a result here is some output. And this output for this particular instance will be zi or zi, whatever you want to call it. So the idea is you have a set of parameters. In a neural network, we would call them weights and biases. In this case, now we can just call them parameters here, or coefficients, you could say. And this is just an ordinary linear regression, right? We get the input, we get some parameters, and then we get an output. This is just a linear combination, very simple. And the dimensions here, we need to transpose that. This is just going to be a single value. This is going to be the logit, or if we have multiple, it's going to be the logits. And the parameters here, now you don't need to care too much about the definition of logits. It's just a word that we use to take that and feed it into another function to get some value. And then usually we take the logarithm. We're going to talk about this in a second. Don't be too confused because of the word logits. It's just the output of this linear combination here. And as I said, we have n features here. And for each feature, we have a parameter. So we also have n parameters. However, that's not exactly true because we also have a bias or an intercept. So thinking about this visually, if you have like a linear function like this one, you can keep it linear, but you can also shift it up and down so that it doesn't necessarily go through the origin. So you can have something like this as well. So because of that, we have also an intercept or a bias, which means that usually we just prepend a 1 here. So we have n plus 1 features actually, and also n plus 1 parameters, so that we have an intercept. And this results in zi or zi. So the output, the logit for this particular instance given our parameters. And to not confuse you, these parameters are exactly what we're looking for. By default, they're just going to be random values or just ones, whatever. It's not intelligent. And what we're trying to do is we're trying to find the right parameters so that we get the right answer. And this is the whole magic of gradient descent and optimization. This is what we're actually implementing here. But you need to first understand the basic idea of logistic regression. So we get these logits, and then what we do is we feed them into a function, or maybe before I already give you the solution, think about what do you have to do to get from this number that can literally be anything to our probability between 0 and 1. So we get a value, something like this. This can go off into infinity, it doesn't really matter. But I need a function that gives me a value between 0 and 1. So here I could have 1, here I have 0. I need to stay within this zone here. How do I do that? I need to find a function that always stays in that zone. So I need to find a function that, I know these are not the most beautiful charts, but I need to find a function that, given any input here on the x-axis, always returns a value, a y value between 0 and 1. And there are multiple functions like this, but the one that we're going to use here and that is usually used is the sigmoid function. Maybe you know about the sigmoid function from neural networks. It's a function that forces the output to be between 0 and 1, and it does that in a smooth way. Now, this is probably not a perfect plot, but you can see what happens here is that we never quite get to the 1. So the closer we get here to infinity, we get closer to 1, but we never get quite to 1. It converges towards 1. And here the same thing, if we go to negative infinity, we approach 0. So yeah, the higher your x input here, in this case, if we're just considering one feature, this could be, you know, hours studied, and this could be exam passed. The more hours you've studied, the closer you get to 100% guarantee that you're going to succeed and pass the exam. And, you know, negative numbers doesn't make a lot of sense in this case, but you get the general idea. We want to take any output, any z value that we can get, and we want to force it to be between 0 and 1. And of course, we can shift this around, but essentially we want to have a value between 0 and 1. And we do that with a function. The function here that I just plotted, or that I tried to visualize somehow, is called the sigmoid activation function, or in this case, maybe it's not an activation function, the sigmoid function, which is defined as follows. If I manage to draw a sigma symbol here, sigma of any value z is equal to 1 over 1 plus e to the power of minus z. So if you use some visualization tool, maybe Wolfram Alpha, maybe some other software that you want to use for visualization, if you visualize that function, you're going to see it looks like this. So it takes any input here on the x-axis, and it gives us as an output a value between 0 and 1. And in the middle here at 0, it's exactly 0.5. And you can see it's smooth, so we can also take the gradient, or we can also take the derivative and get the gradient of this function. And this is what allows us now to take the output z and turn it into the output, let's call it h. So h of I, given certain parameters of x I, is equal to sigmoid of z I. So this would give us the estimated probability. Let's write it down here, estimated probability. So I hope this is not too confusing. Let me just briefly recap this. We have m instances where I is the ith instance out of these m instances. Per instance, we have j features, but this, what I showed you here, is just for a single feature. So this is just the concept in general. What we do is we do a basic linear combination. We take parameters that in the beginning are going to be random or just one, and we take our input features, so hours studied, hours slept, and so on, and we just calculate the product here, the vector product, and we get here the logit z for this instance I. We take that then, because that can be any number, we take that and feed it through the sigmoid function to get a value between 0 and 1, which is our probability, and this gives us our h of x, given the parameters theta. Now, the problem is, since we want to train this, since we want to find the optimal parameters, we need to have something that we can optimize on. Now, this is not something we can optimize. This just gives us the probability that the instance is a positive instance. If we maximize this, we're just always going to get 1 as a result. This is not what we're trying to do. We're not trying to maximize the output of this probability function, because we only want to maximize the output if the actual instance, if the actual correct answer is yes, if the actual correct answer is 1. Otherwise, we want to get 0. So if the correct answer is 0, we want this to be as close to 0 as possible. And if the actual answer is 1, we want to get this as close to 1 as possible. So what we actually need is we need a function that we can optimize, and we're going to start by thinking about this in terms of likelihood. So we can derive, or we can come up with a function like this. We can say the likelihood of the parameters being optimal, we could phrase it like that, is given theta, we want to see the product here. So this is pi, but it's also the product. It's like a sigma for multiplication. So starting at I equals 1, going up until m, so going through all the instances. Remember, we have m instances. What we want to do is we want to say, okay, given h theta for an instance xi, taking that and taking that to the power of the actual true classification, so yi. Now, you need to understand this here is the output of the sigmoid function, and this here is the correct answer. This is always going to be either 0 or 1. This can be nothing else. It can either be 0 or 1. Either the person passed the exam or not. Either this is a cat or it's not a cat. So this is the ground truth. This is the actual answer. And we can take this now and multiply it with the opposite, 1 minus h given theta of xi, and then taking that to the power of 1 minus yi. So what you will notice if you play around with this function here is that if you actually produce a value very close to 1 here, and the actual value is also 1, you're going to get here 1, or something very close to 1. We could actually give it a try in a calculation. So let me open up here briefly a Python console or a Python shell, and let's just try to enter for one instance here a value. So let's say my sigmoid activation function produces something like 0.999, so very confident that the answer is yes. Then I take that to the power of the actual answer, which in this case would be 1, so that would be a correct instance. I take that and I multiply that with 1 minus my classification, so 1 minus 0.999, and I take that result to the power of 1 minus 1, which is 0. When I do that, you can see that the answer, or that the result here is also very close to 1. So that gives us a likelihood of almost 100%, which means that the parameters seem to be very accurate for this particular instance. Now, if I do the opposite, if I say I'm very confident that 0.999, or that 1 is the answer, so I have 0.999, if I take that to the power of, actually, it's not that, it's actually 0, and then I take that times 1 minus 0.999, and I take now 1 minus 0, so that to the power of 1, then you can see we're very close to 0. So if we get things right, we get a number close to 1. If we get things wrong, we get numbers close to 0. And by multiplying them, we do that for all the instances. So what we do is for each instance, we get a number between 0 and 1. Multiplying them together is going to reduce the overall likelihood if you have values that are not close to 1. Every value is going to reduce it a little bit because you're not going to get 1 exactly, because sigmoid can never reach 1. But you get the idea. The more mistakes I make, the smaller the value, the lower the value that I'm going to get out of this likelihood function is going to be. Now, this, however, is not optimal for a couple of reasons. So this likelihood function works in principle, but there's a couple of things that we want to change. First of all, we want to actually negate it. Why? Because we actually want to do gradient descent, and gradient descent minimizes. So we actually want to go the opposite. We are not interested in how well we are performing. We are interested in how wrong are we. So we're looking for a loss function or a cost function. So we actually want to take this times -1 to make it something that we minimize and not something that we maximize, because if we optimize this, we would have to maximize it. We want to minimize it. The second thing is, and I don't want to go into too much detail here when it comes to that, but using the raw numbers here is a little bit problematic when it comes to numeric stability. So we can say it's numerically unstable. And because of that, we want to take the logarithm. So maybe let's also write here the action times -1. We want to take the logarithm, or actually want to take the natural logarithm, so base e. And third thing is we want to scale it. So we want to make it scale invariant. So we want to divide. I mean, this is maybe something that we should talk about once we do the logarithm, but what's going to happen with the logarithm is that the product is going to turn into a sum. And because of that, later on, we're going to divide by m. So we're going to say 1 over m times the expression that we end up with. I'm going to talk about this here again when we get to that part. But these are the three things that we're going to adjust. And when we do that, we're going to get something that a lot of you guys have heard about, but I don't want to spoil that yet. So let's just apply this. Let's start by applying the logarithm. What happens if I apply the logarithm, the natural logarithm? So ln, when I apply this to the likelihood function, what happens is I apply it to the entire expression. Now here you need to know a couple of rules when it comes to the logarithm. When you take the logarithm, either ln or log, whatever base you're using, if you take the logarithm of a product, what happens is it becomes the sum. So that's the same as saying ln a plus ln b. So if you have ln of a times b, you can write it as ln of a plus ln of b, which means that this pi here, this product, turns into a sum in general because I can just rewrite it as additions. And then also I have a to the power of b becomes b times ln of a. Now with these two rules here, we can get the logarithm of the likelihood function, so the log likelihood function. And this is now the following. We say sigma, so sum of I going from 1 up until m instances. And what we do now is we apply the logarithm to the individual expressions. What's going to happen here is, since I have the exponent here, this is going to be yi times logarithm of what I have here. So I can go down here and I can say yi times logarithm of h given theta of xi. Now the next thing is, here we also have a product again. So we have left side times right side. This also turns into a sum now since we're using the logarithm. So we have now plus, and the rest stays the same. So we have here 1 minus yi. This is again the exponent. So we take that times logarithm of what we have in here. So that will be 1 minus yi times logarithm of 1 minus h given theta of xi. So maybe that's not the most beautiful writing here, but you get the idea. We can do it like this. Now, this right here is already the log likelihood of theta. So this is the log likelihood instead of just the likelihood. And now, as I said, we're going to make this scale invariant by dividing over m. And also we are going to multiply with -1 to make this something we want to minimize. So this is going to result in something that we're going to call j of theta is going to be equal to -1 over m. And then we're going to write the same thing here. I is equal to 1 up until m. And that is the resulting formula. Now this here, maybe you've heard of this already. This here is called the cross entropy loss function. This is something we oftentimes use when training neural networks. Oftentimes we choose a loss function. We say cross entropy loss. This is exactly what it is. It's the negative average log likelihood. So this is just another way of saying that. This is the cross entropy loss. And this is now what we want to minimize. This is the loss function that we want to minimize. This is what we're going to use to perform gradient descent and to find the correct parameters. Now, how do we do that? The basic idea of gradient descent is we have our parameters theta, and we need to understand, okay, for each of them, for each theta j, so for each individual parameter, how does this individual parameter have to change in order to change my output to be more correct? So I currently have my predictions, which are my h values, or let's just call it h, and I have the actual truth, which is y, and there's a difference between them. Now, how do I need to adjust every individual parameter j to overall make this difference here to be less. And to be precise, how do I have to change them in order to minimize whatever I get out of here, whatever my loss function produces? And we do that with calculus, with partial derivatives. Now, again, you don't need to be a math genius in order to understand how this works. Don't panic if you don't know what partial derivatives are. Partial derivatives are like ordinary derivatives, just with respect to a single variable. So if you have a function that depends on many different parameters, you can say, how does the function change when I change a single specific parameter, ignoring all the others? So in general, a derivative tells you how a function changes when you change the input. And in the case of multiple inputs, in the case of multiple parameters, you can look at the effects of an individual parameter. So the notation for that is, I have some function, in our case now j. How does j change with respect to something? Like, for example, theta j. If theta j is one of these n parameters. Remember, we have n features. So we have n parameters, one for each feature. And we're asking, how does my cross entropy loss, how is my cross entropy loss affected when I change this parameter j, which could be hours slept, for example. Now, we're not going to do it directly with j. Why? Because we can take a look at j and the log likelihood. Remember, j is just -1 over m times the log likelihood. So j is actually just -1 over m times log likelihood of theta. So the derivative here, the partial derivative, is just -1 over m. We can keep that in mind and focus now just on the log likelihood itself. And to figure out how the log likelihood changes when we change individual parameters, what we need to do is we need to apply the chain rule of calculus. Chain rule of calculus. This is what we're going to apply here. So how do we do that? We look at the log likelihood, which is this stuff here on the right, and we're looking at how it changes with respect to the parameters. For this, what we need to do is we need to say, okay, how does h change with respect to the parameters? And how does my log likelihood change with respect to h? So the first thing I do is, okay, my log likelihood depends on h. So I say, how does my log likelihood depend on h? What is the relationship here? How does it change? Then, however, I also have h, which changes with respect to z. Remember, h is just a sigmoid function called, where is it? The sigmoid function called onto z. So h is just sigmoid of z. So the relationship here is also important. How does h change with respect to z? And then I need to ask, okay, how does z change with respect to the parameter? Because remember, z is just the parameter times the instance. So that is the formula again. So what we do now is we calculate these three partial derivatives, and then we just multiply them together, and then we can also take them again times -1 over m, and then we have the actual dependency here, or the actual effect here, the actual derivative. So we're going to do this here now. I'm going to do it on a basic level. However, the simplifications is something I'm going to skip. I have them here on paper, but I don't want to waste your time here with just doing raw calculus stuff. So let us just take a look at how this works. We have the log likelihood and h. All we have to do is we have to take 1 over h here for the logarithm. We keep yi, and we also keep 1 minus yi. Here we just do 1 over 1 minus h theta xi, and also we do times -1 because we have a -1 here. But essentially, the result for this specific derivative here, you can either calculate it yourself, you can use some computational engine, or you can just trust me. But the partial derivative here is yi times 1 over h. Actually, let's keep it simple. Let's just use the letters only. So it is y times 1 over h plus 1 minus y times -1 over 1 minus h. Now, you can simplify that, and the result is going to be y over h. This is just, of course, multiplication here. And then minus 1 minus y, 1 minus h. 1 minus h. That is the first part here. The second part is kind of easy because it's a well-known derivative. So what we have here for h with respect to z is just a sigmoid derivative. So taking the derivative of the sigmoid function, you can also do this manually if you want to, but it's a well-known derivative. So the derivative of the sigmoid function with respect to z is just sigmoid of z times 1 minus sigmoid of z. That is a well-known derivative. So in this case, what this means is h times 1 minus h, to keep it simple with the same characters here. And then the most trivial one is this one. This is super simple. Why? Because what we have here is just, remember we had z is equal to theta times x. So I just get x, or to be precise, I get x j. Why j? Because I'm only looking at the one feature that I'm multiplying this parameter with. Remember, we're only looking for the effect of a single feature, and this single feature only depends on, or this single parameter, sorry, depends only on the specific jth input feature of x. So here, the derivative is xj. All right, and when we take all of that together, what we get as a result down here is the partial derivative. So the log likelihood function taking the derivative with respect to theta j is equal to all of this combined, y over h minus 1 minus y, 1 minus h, taking that, multiplying that with h times 1 minus h, and multiplying that with xj, ith instance, if you want to specify it like this. And this, again, I'm not going to do it here now on screen because it would just waste time, but the simplification of that, when you do it, and I've done it here on paper, what you get out in the end, this is very convenient, is you just get y minus h, at least for the left part. So this here simplifies to y minus h, and this here then is still an addition, so we get y minus h times xj of I. That is the result. And now you can combine this, you can say, okay, this basically just means that the cross entropy loss, taking the derivative of the cross entropy loss with respect to a specific parameter, theta j, is just negative 1 over m times y minus h times xj I. That is the final derivative here. Now, I'm well aware of the fact that this is not the perfectly clean mathematical notation. There's an I missing here, and it's more about the intuition here. It's not exactly how you would write this. However, it's also not the one representation or the representation that we want to use here. What we actually want to use here is the gradient notation. So we are interested in the matrix form or the vector form of this gradient, which is gradient of j. So gradient theta j of theta is equal to, and now we can write this in matrix form or vector form. We can say negative 1 over m times x, now this is a large X transposed, times h of theta multiplied with x. So this is now the actual linear combination. This is now calling sigmoid on it. So this is actually just calling sigmoid on it. And then we take that minus the actual output vector. So this is now the vector notation. This is not just for a single instance now. This is a matrix containing all the instances. This is an output vector containing all the outputs. These are no longer just individual instances. And what we can do now, of course, is we can get rid of the minus. I can say 1 over m times x transposed. And then I can just swap this. I can say y minus h of theta x. That is that. This is our gradient. And this gives us now the direction of steepest ascent for all the parameters. And of course, what do we want to do? We don't want to maximize, so we don't go into that direction. We negate it and we go into the opposite direction. So what we do is for every parameter, for the vector of the parameters, what happens is we take that times, we take that minus alpha, which is the learning rate. So how much do we want to go into that direction? and we go into the opposite direction of the gradient. So we have the gradient here. What we do is we take that direction of steepest descent, we go a certain point into the opposite, or a certain amount into the opposite direction, and that is our new set of parameters. We do that a couple of times, and in the end, hopefully we have a model that does what we want. All right, now that was quite a bit of theory, and we're not going to need a lot of the stuff that we have written here. The only thing that we really need is the sigmoid function and our gradient calculation. So this is the thing that we're going to put into code. Everything else in between, also the loss function, the cross entropy loss, is not really relevant unless you want to print it. But for the calculation, you just need the gradient, which is derived from the loss function. Now we're going to put all this into Python code. So let's move that to another screen. Let's open up a command line. Let's go to our working environment. And now let's create a file main.py. Before that, maybe you want to install NumPy if you don't have it. So pip or pip3 install NumPy. You can also use uv. So uv init, uv add NumPy. And once you have that, open up a main.py file. And here now we're going to implement this from scratch. So I'm going to just say import numpy as np, and now we're going to put the math that we just discussed into code. We're going to start here by defining the sigmoid activation function. So we're going to say sigmoid of a given value or vector of values z is going to be the following. We're just going to say return 1 as a float over 1 plus np dot exp. So e to the power of, and of course this needs to be in parentheses, np_exp negative z. All right, so we just need that in order to apply it because it's part of the gradient. Remember, in our gradient we have here h, and h is basically just a sigmoid function. So the next step is to take this gradient and to put it into code. How do we do that? We say def and then calculate gradient. Now for this we need a couple of things. We need to have theta, the current set of parameters. We need to have the matrix capital X, which contains all the features and all the instances. And we need to have the vector of the results y. So we have theta, x, y. And then we just have to apply the formula. So we say m is equal to y dot size. M is again the number of instances. Remember, n number of features, m number of instances. And what we do now is we just say return. Now we have x transposed times y minus h of, so minus sigmoid of theta multiplied with x, or in Python notation that would be x multiplied theta. And we take that and we divide it by m. So we say here x transposed matrix multiplication. So this is the at operator. If you don't know about it, this is matrix multiplication. So x transposed at, then sigmoid, and then inside of the sigmoid function, we also do x matrix multiplication theta. We take all of that, so we put parentheses around that, and then we take that divided by m. And actually, I forgot one thing. We also need to put this here into parentheses and say minus y, which is exactly what we're doing in our formula. So that calculates the gradient. Next up, we need to do the gradient descent. How do we do that? We define a function. This is where the whole magic happens now. Gradient descent. For this, we also need to pass now all the stuff. So we need to pass x and y. We need to pass a learning rate, which is 0.1 by default, let's say. We need to pass number of iterations. Let's set this to 100 by default. And we need to set a tolerance. This tolerance is going to be relevant because of imprecision here in the computer. We want to basically terminate the gradient descent process if we don't have a meaningful difference. Now, what did I mess up here? Oh, I forgot to close the bracket up here. So we have gradient descent. There you go. And what we do here first is now we need to prepend the bias. Remember, I talked in the beginning about the intercept, about the bias. We need to add it now because by default, x is only going to have the features and theta is only going to have parameters for the features. So what we need to do is we need to add an additional dimension, which is going to be the bias. So I'm going to say here x with bias, x underscore b is going to be equal to numpy.c, concatenate essentially, so c underscore, and we're going to prepend np ones. So we're just going to add a bunch of ones. And the shape is going to be shape 0. So x shape 0. And we're going to just put a bunch of ones there in this dimension. So per instance, we're going to have just an additional 1 so that we can multiply it with whatever we have as the parameter for it. And of course, we need an additional bracket here because we're passing the shape. So shape 0 times 1. And then we also add here x itself. So we prepend a bunch of ones here, or actually a single one per instance. And then we have our x with the bias dimension. Then we say theta is essentially just a bunch of zeros with the same shape. So the shape of an individual instance of xb, so 1. And that is essentially the idea. We have now our inputs. We have our theta, which starts at 0. And then what we do is we say for I in range, number of iterations, we're just going to do the gradient descent. So we're going to calculate the gradient given theta, given x, given y. We're going to take that gradient and we're going to move into the opposite direction. So I'm going to say theta minus equals alpha times the gradient. That is exactly what we discussed mathematically. Now we're doing it in code. We have our gradient calculation, which we derived from the chain rule of calculus, and then we just apply it, we calculate it, we go into the opposite direction. Now, if the magnitude of change is, or if the magnitude of the gradient is too small, we can just break the loop. So I can say if np.linearalgebra, so linalg, norm of the gradient is below the tolerance, we can just break, we can do early stopping, so to say. And in the end, we return the resulting parameters theta, so the trained parameters. Now, the only thing that we need to do now is the actual prediction. Now, as we discussed, the logistic regression returns a value between 0 and 1, so it's going to return a probability. We define a function predict prop a, as it's called in scikit-learn, so predict a probability, given some x and given the theta. So we don't have the ground truth here, we're just doing the inference, so we're making a prediction. We're going to say x underscore b is equal to np concatenate again. So actually I can copy this from above like this. We're just prepending the bias dimension again. And then all I have to do is I have to calculate h. So h is actually my prediction for the probability. I say sigmoid of x underscore b matrix multiplied with theta. This is going to give us now the probability between 0 and 1. And if I want to have the actual class prediction, I can do the same thing with a threshold. So I can say threshold can be by default 0.5, which makes sense, but sometimes you maybe want to change that. And here we're just going to return now predict probability given x and theta. Is that above or equal to the threshold? If yes, we're going to get a 1. Otherwise, we're going to get a 0. We want to get this as type int, not as a Boolean. And that is the implementation. Now, I'm not sure if I made any mistakes here, but this is the whole idea. This is what we discussed mathematically. Now we have it in code. And what I'm going to do now is I'm going to use an actual scikit-learn dataset, and we're going to use our classifier instead of the scikit-learn classifier, and we're going to see if it performs well. So now we are going to use scikit-learn, but not for the implementation of logistic regression, just to evaluate it, just to see if it works. So we're going to actually, if you don't have it, you need to install using pip or uv. So pip3 install, or uv add scikit-learn. And now we're going to say down here from from sklearn dot datasets, we're going to import the breast cancer dataset. So load breast cancer. From scikit-learn.preprocessing, we want to import a standard scalar. From scikit-learn.model selection, we want to import the train test split. So we have something for training, something for evaluation. And then from scikit-learn.metrics, we want to import the accuracy score so that we can easily evaluate this. All right, and what we're going to do now is we're going to say xy is equal to load breast cancer, return xy equals true. So this splits it into x and y. Then we take that, we turn it into x train, x test, y train, y test. That is equal to a train test split of x and y with a test size of, let's say, 0.2. So 20% of the data is going to be used for testing, for evaluation, so to say. Then we're going to scale the data. So the scalar is a standard scalar, and x scaled, or x train scaled, is going to be equal to scalar fit transform x train. And then since we don't know about the test data in the beginning, x scaled is just going to be scalar dot transform, not fit transform, x test. And now what we can do is we can calculate, or we can do the training. We can say theta hat is going to be the result of gradient descent. So I'm going to say gradient, not NP gradient, gradient descent, given our x train scaled data, given the y train ground truth, and given a learning rate of, yeah, we can just do 0.1 explicitly, or we can just do nothing because the default is 0.1. And then what we're going to do is we're going to say y predictions made on the training data are going to be predict x train scaled given the trained theta hat. And we're going to do the same thing with the test data. And now finally, we're going to get the train accuracy. So how well does the model perform on the data it already knows? For this, we're going to say accuracy score, y train, or y predict train. And then for the test accuracy, we're going to do y test, y prediction test. I'm going to print both. There you go. So let's see if I made some mistakes. Now let's just run this. And I did make a mistake. Oh yeah, because I have a problem with the parentheses. Of course, we need to close it here and then divide by m. But besides that, I have a problem here with this because I should be passing x with a bias, not just x. But now it should work. And there you go. We get the training accuracy of 98.25% and the testing accuracy of 97.36%, which means that this is definitely working. So we can also see what happens if I reduce the number of iterations to 1, for example. This should lead to a worse performance. There you go, 93%. It's still very good, so it just needs a single iteration to be somewhat decent. But you can see that the concept that we discussed mathematically works when we put it into code. We didn't use anything from scikit-learn when it comes to the actual logistic regression. So the whole training, the whole model, everything, the inference is done by us. This is just pre-processing of the data and evaluating. And you can see it works perfectly fine. So this is how you implement logistic regression from scratch in Python. So that's it for this video today. I hope you enjoyed it and I hope you learned something. Let me know in the comment section down below if you like these from scratch videos, if you like these mathematical videos, if you like to see more stuff like this, for example, for support vector machines, decision trees, random forests, and so on. Let me know. Also, let me know if you're interested in neural networks from scratch. There's a bunch of stuff that we can do. Just give me the feedback and I'm going to adjust my content based on that. Besides that, don't forget to hit the like button, subscribe to this channel, and also hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.